Solving the Kepler problem using only Newton's laws, high school level math, and an intuitive approach to the concept of limits. Video 4, Proving Kepler's Third Law. First, we need to review a few things about ellipses. You probably remember that A, shown here, is the semi-major axis, and B is the semi-minor axis. Every ellipse has two foci. Note that B is a perpendicular bisector of the major axis, and therefore the point P, where the semi-minor axis touches the ellipse, is equidistant from the two foci. Now let's recall a defining feature of an ellipse. If you draw a line segment of length m from one focus to any point on the ellipse, and draw another line segment of length n from the other focus to the same point on the ellipse, their total length, m plus n, equals 2a. It follows then that if the pair of line segments touch the ellipse at point P, they must be of equal length, namely, the length of the semi-major axis. The purple, blue, and green line segments shown here make up a right triangle. It is customary to denote the length of the green leg as c. At this point, we can label the segment of the major axis that we know as r sub p, and note that r sub p equals a minus c. With this review behind us, I want to point out three equations related to an ellipse. We will need these three equations to prove Kepler's third law. First, the area of an ellipse is pi times a times b. Now, the eccentricity of an ellipse is defined as c divided by a. So, c equals a times e. Since r sub p equals a minus c, we can say that r sub p equals a minus a times e. Or r sub p equals a times the quantity 1 minus e. This is the second equation that we will need. Finally, since we know that b squared plus c squared equals a squared, according to the Pythagorean theorem, it follows that b squared equals a squared minus c squared, or a squared minus a squared e squared. Leading us to the third equation we will need, b squared equals a squared times the quantity 1 minus e squared. Now we can begin our proof. It should be obvious that if you multiply the period of the orbit, t, by the amount of area swept out per unit time, you get the total area of the ellipse, which also equals pi times a times b from equation 1 for an ellipse. For dA dt, we can substitute its value when the planet is at perihelion. Then we can square both sides. It's starting to look a little messy, but we press forward by multiplying both sides by 4 and dividing both sides by rp squared and by v naught squared. The trick at this point is to manipulate the denominator of the fraction on the right side of this equation so as to get rid of both the r sub p and the v naught factors. Let's start with v naught. We will recall that there are two other ways of expressing V naught, and in a somewhat unconventional move, we will use both of them. First, V naught equals 1.1 times V reference in accordance with the initial conditions that we chose. We subsequently found that V naught also equals 1.21 times capital R, the radius of the dV circle. As it happens, it will be useful to substitute for V naught squared the term 1.1 times V reference times 1.21 times capital R. Let's put our new expression for the denominator in some free workspace up and to the right. We have also found earlier that capital R equals gm divided by the quantity R sub p times 1.1 times V reference. Let's take this value for R and substitute it into the equation above. At first glance, it appears that things are getting even more complicated. But there is a 1.1 times V reference in both the numerator and the denominator, so they will cancel out. And if we also divide R sub p squared in the numerator by R sub p in the denominator will disappear entirely, and we will be left with R sub p times 1.21 gm. Now, as we have seen, 1.21 is simply 1 plus the eccentricity. At this point, we could make a substitution for R sub p based on equation 2 for an ellipse. Multiplying the factors 1 minus e and 1 plus e, we get this expression for our denominator, and we can go ahead now and make that substitution. Now let's substitute for b squared using equation 3 for an ellipse. You can quickly see how to simplify the fraction on the right-hand side of the equation in order to get t squared equals 4 times pi squared times a cubed, all divided by gm. Of course, 4 times pi squared divided by gm is a constant, so we have just proven Kepler's third law that the square of the period is proportional to the cube of the semi-major axis. You are now ready to proceed to video 5, the final exam question.